Hello, this is Kerry Schutz with MathWorks. In this video, I'm going to introduce co-simulation between Cadence Spectre and MathWorks Simulink, and then we're going to walk through a small Hello World example of setting up co-simulation and running it. So this is our small Hello World co-simulation example. On the one side, it involves Simulink running and simulating, and on the other side, it involves Spectra simulating and running. On the Simulink side, it consists of a sine wave source applied to a gain block, in this case 0.75, and then we're just displaying that on a scope. And then we're essentially doing the same thing effectively on the Cadence side, where we are going to develop or create that 0.75 gain factor by way of a voltage divider, where we're measuring the voltage across a 3K resistor that is in series with another 1K resistor. So we essentially have 3 over 4 for the gain factor there. Now, to set up co-simulation in each environment, you need what's called a coupler block. And on the Simulink side, this Simulink coupler block, we are inputting the sine wave to it on the A port. I'm just calling it A here, the input port side. That is going to develop or manifest itself as an ideal voltage source on the Cadence side on the A output port. So you immediately notice that an input on the Simulink side is an output on the Cadence side. And likewise, an input on the Cadence side is an output on the Simulink side. So there's an inverse relationship between IOs, as you might expect. So in any case, that ideal voltage source at A is applied with respect to ground, ground being down here in the lower left-hand corner. So we've got a voltage A applied across R0 and R1. In this case, it would be that sine wave voltage. And then we are going to measure the resulting voltage that develops across R1, which is a 3K resistor. That is, of course, a voltage, again, measured at B with respect to ground. That input voltage then sensed becomes an output voltage, again, on the Simulink side. We're going to display that on the scope right next to the output of the behavioral 0.75 block. So again, our main point of this video is talk first of all, a little bit about what co-simulation is and why you would do it, but then afterwards, really get into the nitty-gritty of how you would set up co-simulation and run a co-simulation model. And before we do that, I just want to mention that co-simulation does scale to much larger designs. Although we're showing a very small Hello World example, it can be used on much larger designs with, let's say, feedback loops and 2 different variable step solvers running in situ and exchanging data, respecting each other's time steps. Here's an example where we have a charge pump and a loop filter that we don't have, in this case, behavioral model of. We're going to be using the transistor level or the circuit level descriptions of these on the Cadence side. So we'll have the phase frequency detector implemented or modeled natively in Simulink, the reference oscillator, the VCO, and the divider. Again, all those modeled natively in Simulink, and then the circuit level description will be handled by way of the Simulink coupler block and co-simulation. And if we were to just overlay those two on the same slide, we would see that this coupler block corresponds to this coupler block on the Cadence side. So we have 2 inputs and 1 output on the Simulink side. That means we've got 2 outputs and 1 input on the Cadence side. Remember that flip-flop relationship. So whatever signal comes in here, notice it's a signal in Simulink, not a voltage, but that's going to correspond to a voltage that's developed for the purposes of this charge pump input. That charge pump input will then develop finally a voltage that's sensed at the output of the loop filter, which you can't see. It's hidden behind our Simulink slide, which corresponds to that red trace here. The red trace here is the input to the co-simulation block, which is an output of our co-simulation block on the Simulink side. And so this is a co-simulation involving 2 variable step solvers working together. All right, so the question would arise then, why would we do this type of co-simulation at all? One reason is it does allow us to bring transistor level detail into a behavioral Simulink model. That allows us to validate the accuracy or confirm the accuracy of our behavioral model in Simulink. Sometimes you model something behaviorally in Simulink, but you're really not sure how close that behavioral model is to reality. And co-simulation is one way to ascertain that as a measure of closeness. Other reasons people use co-simulation, although they're not as common as the first one I mentioned here, is to reuse a Simulink test bench that you already have as part of your Cadence schematic. So you may already have a Simulink test bench with certain types of, excitation, sine waves or chirps or random noise or other custom excitation you develop, and you want to drive your Cadence schematic with that. And likewise, in your Simulink model, you may also have different types of measurements you've already performed using a combination of Simulink blocks, MATLAB code, and display blocks like spectrum analyzers and eye diagrams and histograms. And maybe you want to leverage all that test bench right in your Cadence schematic, and co-simulation would be one way to do that. You can also, with co-simulation, of course, use kind of the inverse of the approach one, where instead of bringing the transistor level detail into your behavioral Simulink simulation, you can bring behavioral models into your transistor level simulation. So really, in some ways, kind of the same thing, but you're just looking at the problem differently. It may be that your transistor level version or your circuit level version in Cadence is not developed yet, and the behavioral version could serve as a surrogate or a stub, some temporary means to work around the fact that you don't have that circuit level version just yet. It is important to keep in mind that co-simulation, while powerful, it's not a panacea. It doesn't solve all problems. So it's a powerful technique that involves two simulators running in conjunction, but it is a frequently misunderstood, underutilizing, and challenging tool. It's misunderstood because many people think that it is a panacea, that I can just always get the best of both worlds with a circuit level schematic and a behavioral model and kind of problem solved. It's underutilized because many people aren't aware of co-simulation to begin with between the two environments, and or maybe they heard about it, but they've never really tried it, don't know much about it. And it can be challenging to set up the first time if you've never been exposed to co-simulation. There's kind of lots of steps in the process. So just keep that in mind about co-simulation. It has to be properly applied. Co-simulation, while powerful, again, is still much slower than running a pure behavioral model, because that circuit level model, that transistor level model, is higher fidelity, and higher fidelity always comes at a certain price. That's usually meaning simulation time price, the wall clock time it takes to simulate such a detailed model. So behavioral models definitely have their place, and transistor level models, of course, have their place. And sometimes the combination of them have their place. But running them together is meant to be really a temporary means to improve or verify the accuracy of your behavioral model. It's not meant to serve as a permanent replacement for a behavioral model. And again, keep in mind they can be tedious to set up initially if you've never run a co-simulation before. And that's part of, again, the purpose of this video, is to kind of ease that out-of-the-box experience with co-simulation. Also, remember, there's only one co-simulation block allowed per co-simulation. You cannot sprinkle a bunch of co-simulation blocks in a Simulink model or in a Cadence schematic. It must be one contiguous part of your circuit you're co-simulating, and that's going to correspond to one co-simulation block per co-simulation. All right, so now it's time. Let's go ahead and step through a co-simulation example from the configuration all the way through running a co-simulation. Okay, so now we're over in Virtuoso. I am on Linux running under an AWS instance, and I'm going to open up my design. I'm going to start with the co-simulation configuration on the Cadence side, and then later we'll get to the Simulink side. So I select PLL CoSim as my library, my simple divider, voltage divider circuit, and then I'm going to open up config view in edit mode. All right, here's my simple schematic. I've got a 1K resistor stacked on top of a 3K resistor. I'm going to be applying in co-simulation some voltage across the combination series connection of those resistors. Before I do that, I'm going to launch the plugin under mixed signal options called AMS. Now, when I do so, you're going to see a couple new menu items appear along. You notice it's options, Windows help. You're going to see that change a little bit. So go again, launch, mixed signal options, AMS, and you see now hierarchy editor AMS appear. From there, I'm going to select AMS. I'm going to go to Simulink coupler creation. I'm going to write this coupler to my PLL CoSim library. It's going to couple in the analog domain. There's going to be one input, one output pin, one output. Notice you can have up to 1024 input and output pins, or possibly you could have 0 if it were only going to be, let's say, a source only or a sync only block. So in my case, it's one input, one output. It says there's a symbol direction mismatch. Do you want to recreate the symbol view? I'll say yes. And at that point, it's created a coupler, however, it hasn't instantiated. To do that, I'm going to right click in my schematic. I'm going to say add instance. And then I'm going to say, yes, it's from the PLL CoSim library. It's the coupler 1_1A. That would be, that's just the notation it uses. That's the coupler block, one input, one output. View a symbol. I'm just going to give it some name. You can call it anything you want here. I'll call it CoSim block. And the other thing you want to make sure to pay attention to is the socket port number. You want to make sure that it matches however you set the socket port number up on the Simulink side. I'll just change it from the default, make it 4. Notice when I did that, it immediately created an instance of the CoSim block, coupler block on the schematic canvas. So I'll just say hide, go over here, connect it up, just left click to connect it to your schematic. When you do that, it's going to create another instance automatically. You can only have one coupler block in a schematic or in your model, so it makes no sense to instantiate two. So I'll just hit escape on the keyboard to cancel that. Second insertion. Notice when you highlight it, confirms that your socket port number is 5024. There's a simulation response timeout of 120 seconds or 2 minutes in case there's no communication between Simulink and Cadence. And then I have an initial coupling voltage output of 0 volts. You could change that if you wanted to. I'm going to leave it at the default of 0. All right, at that point, I'm going to do a check save on my schematic. Then I'm going to go over to my hierarchy editor under the view menu and select update. Notice it says needed there. I'm going to select that. If I go under it again, it doesn't say needed anymore. Now I can go back to my schematic. I'm going to go under launch. This time I'm going to select ADE Explorer, open an existing view. At this point, you don't need to change anything. It's going to be PLL CoSim Simple Divider Maestro view. And that's pretty much it. I'm going to say OK. And that's going to open up. Now, my ADE Explorer in editing mode, and I can go from there. Now we've got the Virtuoso ADE Explorer editing window up, and what we're going to do now is a few setup options here. We're going to go to the setup menu, make sure our simulator is set up for AMS, and it is. Make sure it's not Spectra, but AMS. Second, we're going to go to the session menu and load a particular state. We're going to load this AMS state 1. In this case, I don't need all of these selections here. I'm going to just clear them out and say apply, OK. Okay, now after all that work, we are set up to run a co-simulation on the Cadence side. So we could start now by going to the simulation menu here and hitting run. However, we haven't done anything on the Simulink side yet. So before we hit run here, let's go over to the MATLAB side and do the corresponding setup. All right, on this side, I'm going to open up a model which at this point is generic. It has no association with Cadence or co-simulation, but this is going to be my starting point. And we could, now at this point, if your system is already set up for co-simulation, you could just go here and type SimCouplerModule. And if it's this library is on your path, you could take this block and drag it into your model. Okay, that could just be something you just drag over into your model. That's nice, but in many cases, that block is when you first use Cadence co-simulation, it won't be on your path. So you could say, okay, I'm just going to drag that from here over to here, go into my model. I'm going to connect it up, and we're good to go. Okay, but I don't want to make that assumption that that's going to be the case for you. And there's going to be, of course, setup on this block that we could do, but I'm not going to get into that yet. What I'm going to do right now is I'm going to operate into the assumption that this library, if you type SimCouplerModule at the MATLAB prompt, it'll come back and said, unrecognized function or variable. You would probably get an error there. So that block, in order for it to find it, has to be on something called your MATLAB path. And if you go, I'm just going to open up Path Tool so you can see the MATLAB path and or edit it, change it, add, remove. So for instance, here I have something, this very long path here, home, MATLAB, Cadence installs, etc. And this path is where that SimCouplerModule library that I showed you resides. So I had to add that manually to my MATLAB path. Then the question is, now that you know how to add some to your path, how do you find that path to begin with? And that can also be a challenge. And what I did in my case was, unless your system administrator, the person who handles your Cadence tools, he or she could probably tell you. If they're not accessible, you can always go to your file explorer in Cadence or in Linux, and you could click and then make sure you're it's some home or root path to search. You could click on the search bar, type sim, that same name that we saw a moment ago, SimCouplerModule. I'm going to leave it without the extension, and there's a reason for that, or without the file extension. And you can see in the lower right hand corner that it is busy searching. So I'm going to let that search for a little bit, and you notice immediately something comes up, SimCouplerModule.slx, and the path to that. And there's a few other variants. There's _old.mdl, SimCouplerModule.mdl, mdl.r2008a, and another SimCouplerModule.mdl. So real quick, in case you weren't aware, the SLX is the newer Simulink extension. Been out around 10 years or so. And then the MDL is the older Simulink extension. So it's a text file format, where the SLX is a binary file format file. So in my case, what I'm going to be using is the .slx. However, you probably won't see that on your system unless you created it special. So what I did was I took the MDL library file and I just resaved it in the current version, and I resaved it as an SLX, the newer format. It doesn't matter. Actually, you don't have to do that. You can use either format. You can use the older MDL format or the SLX format. They're both supported. Just let you know why you see that. And you also see that I've got a couple or two .mdl versions. I've got one in my incisive 152 path, and then I've got one in my I've got another one, let's see, the old one here in my 2209. So what I'm using is the Excellium 2209 version. I took the MDL version and just resaved it as SLX. Okay. So if you noticed again that path there, that is the one I placed on my MATLAB path using Path Tool. Okay. So once you do that, you can then bring up the SimCouplerModule. You can type this, it'll find it, and then you can drag that block into your model. Now, it turns out there's even an easier way to do that. Once you get this on your path, there's an easier way to, shall we say, get this into the model. Sometimes, bringing up both the model on the screen at the same time, if you have a lot of windows open, and having this open on the same screen at the same time, your model, it can be kind of a challenge. This is a fairly simple case. But one thing you can do to make your life easier going forward, so you don't have to even remember this name, this SimCouplerModule name could be also just difficult to remember, is you could add it to your Simulink library browser. So I'm just going to bring up my Simulink library browser. You can also navigate to it from your model. You can go to your model and just click on that library browser icon, or you could just type Simulink library browser. That'll also bring up the same window, the same library browser. And you'll notice in mine, in addition to Simulink and communications and controls and signal processing, I've actually got something called Cadence stuff. Now you won't again see that on your system. I added it special as a convenience in order to find this block. And in this case, I can just, you could open that up. In this case, I can right click. Now, the benefit about having it in your library browser is you can just right click on it and say add block to model simple test bench. And that's the easy way to do it. And then you can wire it up. Then the question, I'm begging a recursive set of questions here, is how do you get that in your Simulink library browser? It turns out that's not very difficult. I'm going to go to the path where that library resides, which is here, the one I added to the path. And you'll notice there I have a slblocks.m file. If you create a file called slblocks.m, put it where the library resides, make sure, therefore, it's on the path, on your MATLAB path. Make sure it's named accordingly. Basically, everything typed exactly like here. And then specify the name of the library, browser.library equals SimCouplerModule, just like that. And then whatever you want to call it, however you want it to appear in your Simulink library browser. I called mine Cadence stuff. You could call it something else. Save that file. Again, that's going to be on your path since it's in the same directory with the SimCouplerModule, so it has to be on your path. It doesn't have to be in the same folder, it just has to be on your MATLAB path. And then, in order for it to appear, you could either restart MATLAB or you could type rehash if you don't want to restart MATLAB. Retype rehash toolbox cache. Execute that command. It takes a minute or so to run, and then it will refresh your Simulink library browser. And then from then on out, you can just see Cadence stuff and then work from this. You could, browse it. You could right-click on it to add it to a model, etc. Just makes it much easier to find and manipulate. All right, so now I've added this block. I'm going to close my library browser. Now I've added this block to my model. I need to wire it up. And I need to configure it, just like any Simulink block. There's one input pin, one output pin. I'm not in frame-based mode, so I'm unframed. I'm sample by sample. Frame size inherit, but there's no frames. Sample time, -1 because I'm doing everything analog. So it's a variable step solver, so the sample time is not a pre-specified thing. It's going to vary over the course of simulation. There are some advanced options, and one of those is a very important option, and that is to make sure that the socket port number matches between Cadence and Simulink. And if you recall earlier, I had set it to 5024 just to be a little different from the default. Same timeouts. That is, if you don't get communication between the two environments, it'll time out after a couple minutes. And that's pretty much it. You don't really need to change anything else here to get it running. So I'm just going to say apply, OK. And at this point, well, if you recall, also one more change to the model. I didn't have an equal voltage divider. I had a divider of 0.75. So I had that resistor 3K, and then there's a series combination of 4K. So it's 3/4 or 0.75 for the voltage divider. The sine wave block, if you're curious, it is set up for, I think it's a 1 kilohertz sine wave. This is in radians per second. So that's why you see the 2 pi. And let's see, a sample time of 1e-4, which corresponds to 10 kilosamples per second, or 10x oversampling. All right, so now we're set up to run. We should be equivalent, or at least close to it, of what the Cadence side is doing. We can start the co-simulation by either clicking play here and then go over to the Cadence side and hit simulation run, or we can start on the Cadence side and then go over here. Flip a coin. I'm going to start on the Cadence side. I'll go over here, simulation. I'll go to run. And shortly thereafter, so many seconds, we should see a dialog or a logging window appear here. At that point, you're pretty much okay to go over to, you're sure that something's happening. I'm going to go over here and hit play on the Simulink side. And then at some point, the scope will open up and we'll be comparing the results of the Simulink operation with the co-simulation. Here, we're about done. You see, we're about done with the compilation process on the Cadence side. And then we'll start seeing some simulation progress output about right here. You see the simulation progress. It's running. It looks like it's complete. It's pretty fast. And then you can see I didn't do, a subtraction and looking for a difference. I didn't get that precise, but you can see just by eyeballing it that these two waveforms, from Simulink and from the co-simulation are essentially the same. We could be more robust about it, but this is just a quick and dirty getting started example. And that's about all I wanted to cover really on, the how-tos of getting started with co-simulation. Okay, so how about getting more support on co-simulation? Well, the first thing to realize is that while I represent MathWorks, this is a Cadence developed capability. They introduced this capability back somewhere circa 2007. MathWorks' role here is more of one of raising awareness and hopefully making it a little bit easier to get started with co-simulation. However, as far as officially supporting it or developing it, modifying it, bug fixes, etc., that would all be handled on the Cadence side, not the MathWorks side. So for more, advanced support, you should really either contact your Cadence rep, that person on the Cadence side, or you can go to cadence.com and their online support portal, which I provided the link for here. You can click on their 24/7 Cadence online support. One of the things you can do is then search on different types of documentation. One of those would be on this co-simulation capability, which I've provided a screenshot of here. Once you have that up, you can also download, view the PDF version of it. It's a file by default named amsd.matsim.pdf. It's 103 very detailed pages of reference documentation and examples showing you how to use and set up co-simulation between Cadence Spectre and MathWorks Simulink. All right, I hope you found that helpful, and thank you very much for tuning in.